Very good. Hi, my name is I'm going to give a presentation called NASA Operational Simulator. This presentation was given this past summer by one of my colleagues, Scott Zimrick, at the Speed Defense Security and Sensing Conference in Maryland. So I want to walk through this presentation. First, I'd like to give a little bit of background information on the Independent Test Capability Group, the JSTAR Laboratory. Additionally, then I'm going to walk through and describe what is the NASA Operational Simulator, otherwise called as NOS. I'll go through the architecture and the middleware, a couple of the main components, and then I'll discuss some of the primary use cases or utilization of this architecture and associated tools. So first, the Independent Test Capability was a group that was formed a few years ago to acquire, develop, and maintain or manage adaptable test environments to enable dynamic analysis on multiple missions. The way that this group has approached developing simulators and test systems is basically one of three ways. One is to acquire a simulation environment or test system from a development project. Two is to develop in-house these simulation or test systems. Or third is the actual physically access or go to centers or facilities to utilize test systems. What this presentation will talk about with NOS is what is the common technologies across the projects we develop test systems for, and this is referred to as NOS. So as far as the charter, a little bit more detailed as far as what does the ITC team do. Basically, the ITC, in regards to in-house simulators and test systems, is the team basically does a couple things. First and foremost is a large amount of time is spent in modeling hardware components or electrical components of systems to create environments in which the software can run. Secondly, the team does a lot of simulator and software integration through the development of in-house developed simulators or by acquiring simulators from development projects. We provide a means and mechanism to make these simulators work together in an integrated environment that a user can use to support their work. As far as the NOS architecture, it has been in work as far as a means to group all the common and reusable components across these projects. The third area is test automation. As a program, as we continue to develop, test, and exercise systems via test cases, we want to be smart in the way we exercise these systems. When we create a test, we want to write it manually once and then automate that test for all future executions. Typical users of these capabilities are verification validation teams, IV&V teams, project developers, and in the case of Discover, operators and testers. To deploy these simulators and test systems, the JSTAR or John McConnell Test and Research Laboratory was formed a few years ago. It is a cloud-based infrastructure that utilizes a combination of server and desktop virtualization. The reason that we use virtualization is basically so it's easier to maintain from a central location with the server virtualization, and as a desktop virtualization, it gives us the ability to deploy these complex systems on laptops or personal computers. The lab also supports large-scale simulator deployments, includes hardware-in-the-loop and software-only test environments, and provides essentially an environment where you can integrate commercial tools, government off-the-shelf tools to support verification and validation activities. So now that I've given a little bit of background into the test capability and the JSTAR lab, I'd like to go into a little bit of NOS background and then describe what NOS is. So first, the two projects that the NOS architecture and associated tools were developed was initially as far as the original system that was developed was the GPM operational simulator. And from GoSim, a lot of utilities and the middleware was developed and really instantiated. And then through the development of a secondary simulator, the James Webb Integrated Simulation and Test Environment, the technologies were matured and basically validated that they would work for multiple systems. In addition, not pictured on this slide, the NOS architecture and middleware and associated tools have also been used to support a recent release of the Discover simulator that was released this month, just a few weeks ago. So now I'll go into what the NAS operational simulator is. First, basically, I'd like to define this term and what it means. Basically, NOS is a software-only simulation architecture. It is a set of common components from all in-house or IV&V program software simulation development efforts. It's basically all the reusable components from the simulations that we've developed in-house. The system is capable of executing unmodified flight software executables. This is extremely beneficial in the fact that we don't have to maintain multiple versions. We can compile one time and run the actual flight binary, which is very important for an independent organization. We want to make sure that the actual flight software, as loaded and ran and executed, is what we look at. Within NOS, there is a custom-layered architecture middleware. It's referred to as the NOS middleware generically. Also, you've heard it called as ITCSB, or Independent Test Capability Synchronous Bus. Within this middleware, there is a dynamic intersection capability, which I'll talk to a little bit later. Also within NOS, there's a set of reusable software modules and scripts, which facilitates and makes development of simulation systems much more easy. And then finally, really not a feature, but just basically an end product or end all as far as what all these features give us, is they give us the opportunity to deploy systems using virtual machines. On the bottom here is basically just a very generic diagram in regards to the space domain as far as how the architecture is deployed. You see your test driver, and in most of our cases, the ground systems interface with the NOS middleware, and then from the NOS middleware, we interface with virtual computing platforms, and science instruments, environmental simulators, and external simulators via simulated buses. Sorry, this slide is actually a little bit animated. I've got two animated slides that won't work, so I throw a lot of information up here at one time, but I'll start at the upper left-hand corner of your slide and just briefly walk through the NOS feature set. First and foremost, there is the notion of plug-and-play hardware models. There's been a significant amount of effort to develop hardware models of electric components using basically a device modeling language that allows you to model hardware components. This is basically to build up, and through this we are building up a reusable set of hardware models that can be used on a mission-by-mission basis to facilitate the execution of flight software. Secondly, NOS utilizes, in all cases, or in expected all cases, the use of operational ground system software. Basically, this is the actual ground system in the GPM system. It was the Dynamic America Assist product with James Webb. It was the Eclipse CCTS that was from Raytheon, and then with Discover, it was the ITOS ground system that's now managed by Hammers out of Garvin. In addition, the NOS feature set also includes an instrument model framework, whereas if we do have simulators that we need to put together quick and dirty, we do have simple skeletons or frameworks to create these pretty rapidly. As far as to be able to see the behaviors and the traffic on 1533 buses and spacewire networks. Additionally, I'll talk about the NOS middleware a little further, but here it's just basically highlighting that this is a layered architecture, and on top of the specialized layers, we actually implement specific protocols like MIL standard 1553, spacewire, and discrete communications. And once again, all these features together, due to the fact that these are software-only simulations and test environments, we can deploy these environments via the cloud, via laptop, or via even a thumb drive. So in regards to the NOS middleware, basically what this is it provides a means or a reusable mechanism for communications in a simulated system. It's basically used to ensure consistent and correct data passing among your distributed simulation components. It provides synchronization between the distributed applications, whereas so if your simulation components are running, they basically remain locked. They keep their own notion, remain with the notion of time, and keep going forward together. The design is flexible and extensible and can be extended to incorporate any communication protocol. Like I said, I mentioned the couple protocols that we've supported so far due to our work within the space domain. We've also done some prototyping with CAN bus just to kind of see if make sure that everything would work, and that was successful. As far as features of the NOS middleware, it is transport agnostic. There is a cross-platform C++ implementation and an API for users to utilize the technology. The specialized user API layer is there that we've developed so far. And also, just to mention, which I'll show a slide on here in a minute, interception allows for verification, validation, analysis, whereas there is no modification required to the system under test. So if we take a look at the NOS architecture, it just disappeared from your screen because it just did mine. You guys see it? Well, I can't see, but let's see how we can do it. So basically, what you can see at the base layer is this is the transport layer. Basically, the current implementation is socket communications. Above that is where the magic happens. This is the middleware layer, the core of our middleware that provides the behavior and the synchronization points. On top of that are your protocols as needed, and then that interfaces with your system under test. As far as system monitoring at the layers, there's multiple layered system monitoring. So if there is a problem with the middleware, we can actually look and see what that problem is and debug that problem. This also gives me a slide. Basically shows the dynamic. You normally see that the conversion to PDF, but basically what this shows is three things. One is if you saw the animation, it would show normal data. Whereas you have node A, for example, a sensor, and node B, for example, your system or your software system that you're looking to test. Normal data node A and node B. With the notion of creating a software instantiation of an interceptor, you can basically intercept or block that data without node A or node B knowing what has happened. Also, when you do this, this is a dynamic addition to the system. So it doesn't create, you don't have to make a change to node A and node B, which is beneficial. The next two slides are utilities that have been built upon the middleware. The 1553 interface, whereas you can also do the interception. You can also view your remote terminals and subaddresses. Also a spacewire interface, very similar, just a different look and feel because of the spacewire network. You have the same similar type of capabilities for spacewire communications. In addition, switching gears a little bit, a couple other utilities or features of the NOS architecture. One that we really can't take credit for, but what we wanted to put on the slide is a virtual oscilloscope. One of the commercial products that we utilize gives us this capability to actually be able to see input and output signals and tell if they're raised or lowered. Which is just really nice as far as debugging and knowing what is going on with signals within your system. Secondly, we developed a standard 1553 bus, whereas we can create bus schedules with XML-defined schemas, and we also have the remote terminal, creation of a bus model. In addition, we developed, for this bus, we developed a PASS 3200 software emulator. This emulator was actually developed not first and foremost, but for the use of James Webb to support build verification testing. The development project utilizes the PASS 3200 hardware quite often to do a lot of the build verification tests. So in order to support the IV&V project's needs, we needed to replicate this functionality in software so they could run those tests as well. And finally, as far as the software utilities, there is a virtual spacewire router. So next, I'm just going to talk a little bit about how NOS has been used and deployed to users. NOS is one thing for making deployment. NOS is basically what we've called these reusable components. It is not something a user would see or even know about. It is basically the internal workings or the backbone of this simulated system that makes development of these systems easier and for future projects. So as far as utilization, three projects that utilize this NOS architecture. The first is in the GPM operational simulator, whereas the system was utilized by three entities. First is the GPM flight software testers. They will basically use this, reduce the time required to use lab resources. If you're familiar with the GPM project, there is a couple different hardware labs that they utilize, and this provided a nice platform for them to be able to dry run test procedures where they were needed to use those hardware assets. As far as second group that utilized Ghost is the GPM software safety team. They use it basically as a toolkit to support safety studies. Um, the third user was of the GoSim product was essentially the GPM IV&V engineers to basically do independent testing and risk reduction and to provide really a flexible platform to look at adverse conditions. And also, I'd say the biggest use of the GPM project was to validate findings from analysis. Secondly, GIST, which is an active ongoing project, really has helped the development team the use of NOS in the fact that to develop a much more complicated system, if we didn't think about knowing that we had to do this for multiple projects from the beginning, the NOS architecture and utility saves significant time. And for those of you who are familiar with James Webb, the architecture compared to the first application of NOS and GPM is significantly more complex. There's a lot more simulated components, there's a lot more interactions, there's a lot more buses, and it reduced our time as far as the initial baseline simulator as about half amount of time required to get that first release out, as it did with GoSim, because of the work that we're calling NOS. Secondly, as far as the James engineers, they recently began using GIST. First and foremost, probably the primary thing that they've been using it for now is to support processor offline mode test efforts. Also looking at the redundant command and telemetry processors to look at their behaviors. Recently, I know their IV&V team has verified that some of the behaviors from the offline command and telemetry processor actually was using the same application ID as the online processor, and was able to verify that was the case by looking at that app ID at the ground system. So they could verify and say, hey, this is definitely an issue, and we've got proof, and here's the associated test that we ran to show or demonstrate. And then last but not least, I just want to mention is Discover project, the simulator that's being developed for a mission operations center training platform. Utilize the NOS utilities in the middleware, and basically has provided the platform for developing that simulator. So now just the last thing I'd like to do is just walk through a little bit more information on each of these simulators or test systems, just to give you a little bit more feel of what these systems, what they encompass and what they include as far as simulation. The GPM operational simulator has really, I'd say, 6 primary components. First is a COTS emulator that allows us to emulate the actual target flight processor. We have a set of primary instrument simulations that were developed in-house using that framework that I talked about earlier. Utilize the unmodified GPM ground system. GoSim utilizes the Goddard dynamic simulator, which gives us basically an environmental simulator that's used to support their development activities at Goddard for these projects. And NOS middleware and GPM hardware models that were developed with that device modeling language to simulate the electronic components. Some of the capabilities that GoSim, to highlight for GoSim, are the ability to load and run unmodified flight software binaries and execute flight software test scripts. Also gives the ability to single-step debug through code and inject errors via the ground system as well as the NOS middleware. One thing just to mention, with the GoSim technology, it was also awarded the NASA Software of the Year Honorable Mention in 2012. The funny thing is, when we gave that presentation for Software of the Year, a lot of things that were highlighted were called GoSim, but they were generic in nature and essentially is why we called these things NOS. So just a little history of why that came about. Second is the James Webb Space Telescope Integrated Simulation and Test Environment. is very similar as far as the way it's deployed. Instead of simulated components that run on a set of virtual machines, it is also a software-only spacecraft simulator that is a flexible environment to support V&V activities and also can be used to support other activities. It does also run the unmodified ground system and scripts, unmodified software under test binaries, and it's essentially a large integration of commercial tools, government off-the-shelf tools, simulators developed by Goddard, simulators internally, and simulator and commercial applications. There are also components that's included in GIST. And then last but not least, one thing to mention that I talked about earlier that the team does is GIST has also provided an automation testing framework to be able to hook into and run tests automated through the use of build servers at the build verification system test level. Traditionally, that's often done at the unit testing level, especially with our internal development processes. But we've basically found a way or worked to develop a way to bring up the entire GIST system, execute its test, log the results, and then bring down the system and then run the next subsequent test. This slide basically just shows typical deployment of one of these systems. Like I said earlier, you do not see a NOS mentioned. Like NOS is at the background. The deployment shows, in this case, a series of 4 virtual machines that would be typically deployed for GoSim, for example. And this is basically just a screenshot of vCloud running in the lab. You can see there on the left bottom is the ground system interface. There's also the second virtual machine image is the environmental simulator, or GDS, and then the final image is the flight software running under the COTS emulator. There's also an additional virtual machine here just as far as convenience sake is in build environment, in case you'd like to make modifications to the flight software and load that image within the test system. So basically what I've walked through during this presentation is an overview of the independent test capability and the JSTAR lab. I then walked through a description of NOS and what that is, what that means, and then showed a couple utilizations of the NOS architecture and software applications. As far as NOS, it does provide a generic software-only simulation architecture that has been utilized and demonstrated in multiple NASA missions. It provides the IV&V program with a mechanism to support the development of future simulated systems or test systems for use by IV&V projects. NOS, the architecture is transparent to the user. One thing to mention is for new instantiations of these technologies, they do require customization for missions and projects. Missions are different. They do utilize different simulated systems and environmental simulators, and there is customization required to utilize these technologies. However, these technologies significantly decrease the cost and time savings required to set up test systems. NOS is continuing to develop reusable hardware models that can be used on other projects and missions. And NOS also provides custom developed middleware with user application programming interfaces and dynamic interception capability. NOS also extends to other domains. Typically, NOS has been applied to the space domain, but can also be applied to other domains where you have simulated or embedded systems that you'd like to integrate. Just a couple of contact information. Right here is a web page that has some more information on and about the team and the JSTAR group and the lab. There's also an accompanying white paper that walks through this probably a lot better than I did, but it'll give you a detailed explanation of NOS, the features, and also the utilization. It's very similarly organized to this presentation, and gives you a little bit, like I said, a little bit more detailed information with some examples scattered throughout. If you have any questions, feel free to, afterwards something comes up, my email is there, and also the team mailing list is listed there as well. That's all I have. Are there any questions? Yeah, that's correct. And actually, that's pretty much how the team and the groups operate. We do what makes sense on a project by project basis. In the case of NPCV, we've actually do the same exact thing. There's three simulated environments that we currently bring in house, and this team basically brings those in house, sets them up in the lab, and deploys them to users. And actually, I think Ricky's going to give a presentation a little bit about that in about 20 minutes. He'll talk about their utilization of uh, simulators that are actually brought in-house like that and developed and deployed. And basically, our job is to make sure that the systems match the developers, that the IV&V team has access and can utilize those systems efficiently and effectively. As far as the NOS is basically just focusing on the efforts that have been done in-house. And for those two systems, there was not a cost-effective way to get access to those test systems. We thought this was the most cost-effective approach. Because James, that that that's correct. That is correct. Yeah, with GPM there was hardware assets. There was the potential to actually work at Goddard and utilize those through scheduling that time if that was work with the project. But because of some successes of previous efforts with some of these commercial products and demonstrated ability to be able to set up systems, um, this technology was basically developed under GPM, and then, like I said, further James Webb, and has also been demonstrated as of recent on Discovery. Yeah. Actually, very well. We basically, we actually do some scripting to deploy now using some Puppet scripts. We actually deploy the system using those scripts. We typically deploy usually on a desktop first to do testing and checkout, and then we'll actually write those scripts to deploy to the server. And it's worked fine. Actually, yeah, we like it. We do like it. And just a note, I think it's Mary, right? On Mary's comment too is as far as one thing that's gained that we don't often talk about is during the development of the simulators, working with the IV&V teams, specifically on James Webb, we found several issues in the ICDs because we utilized those to develop the hardware models. Early when you're doing integration, we often use the developer test to validate the system itself. Uh, when we do that, we often find a lot of issues and communicate those through the IV&V team uh, together to get those to the project. So there's definitely some side effects of developing these systems, uh, which we haven't looked into a heck of a lot. We just kind of, as we go, we report those.
All right, we're out of time for Justin's presentation. If there are any questions, you can make them available in the breakout room. We're going to take a 15-minute break. We'll be back at 2:45. Next is Ricky Beamer. Okay.
Okay.
Yeah, the latest schedule is available on our website.
Okay. I printed out the